AI systems are mapping out solutions to extremely difficult, open-ended search tasks. Neural networks reliably navigate combinatorial spaces that historically resisted brute force computation. This capability reached a clear inflection point when AlphaGo defeated Lis et al. A machine conquered a domain previously thought computationally out of reach by layering deep neural networks with structured tree search. Public discussion often interprets these benchmark victories as evidence that hard, worst-case search problems are becoming uniformly easy. However, deploying massive test-time compute or multi-agent debate is different from discovering a universal polynomial time solver for NP hard search. The classic boundary between tractable and intractable computation remains intact. To accurately define what these modern models are achieving, we require a formal language that operates independently of the P versus NP question. Modern AI systems improve through inference time scaffolds. Instead of a single-shot prediction, the system runs finite loops of retrieval, tool use, and self-correction. These scaffolds represent a highly structured, mathematically rigorous form of bounded progress. Computer scientist Chien-Ping identifies this recurring pattern as staged ascent. Staged ascent maps these bounded inference layers directly onto the polynomial hierarchy, which serves as the classical invariant of bounded verification depth. This framework provides the precise mathematical invariance needed to categorize and prove inference time model improvements. The baseline computational regime is P, direct polynomial time decision. In machine learning terms, this equates to a standard end-to-end predictive model, returning an answer without an auxiliary witness or challenge. The first widening beyond direct decision is NP. While the model might not find the correct answer natively, a polynomial time verifier can check a bounded candidate witness once it is proposed. This diagram shows the result of chaining generation and verification stages past NP. The loop starts with a proposal block, an existential quantifier. Next, a universal quantifier block acts as a bounded adversarial check. Finally, a repair block pipes into a polynomial time checker. This structure is formally defined as a bounded guided verification protocol. It aligns perfectly with a specific depth level in the polynomial hierarchy. Every time engineers add a distinct layer of test time debate or repair, they are constructing a deeper alternating quantifier block securely contained below polynomial space. To translate these theoretical protocols into concrete deployments, the framework models an AI artifact as a deployed stage. This formula defines a deployed stage mathematically, packaging depth, polynomial bounds, null support state, exposure relation, and core predicate. The variable K measures verification depth. The core predicate is the engine, operating as an existential start verification mechanism. This definition is strictly bounded. Prompt accumulation, KV cache expansion, and retrieval state are treated as internal channels within one deployment. They do not increase the formal hierarchy depth. Simply injecting a larger test time compute budget inside the exact same reasoning scaffold does not constitute a new deployed stage. Despite highly dynamic, adaptive test time behavior, a system's underlying structural depth remains rigidly fixed, unless developers ship a distinctly new bounded verification stage. We need to distinguish between a system's baseline capability and its absolute theoretical limits under maximum bounded exposure. This central circle represents native reach, solvable instances when operating strictly with a null support state. The larger outer boundary is the closure frontier, representing maximum capability with bounded external context. Points in this ring represent instances solvable via conservatively exposable transcripts. This closure frontier is absolute. It mathematically cannot escape the verification depth of its core scaffold. To properly compare two successive AI deployments, evaluating their default native reach is insufficient. We must evaluate whether the new system actually breaches the absolute closure frontier of the old one. How do we mathematically prove that a newly deployed model version is structurally superior to an older version? According to Proposition 6, if the new system's native reach successfully exceeds the old system's closure frontier, unconditional math dictates exactly one of three structural novelties occurred. This logic gate maps three breakthrough explanations. First, depth gain, adding a new verification block to move up the polynomial hierarchy. Second, same depth core authority, Inference depth remains identical, but the core predicate strengthens. Third, a genuinely new exposure interface changes how models ingest data. This gives us a precise theoretical vocabulary for internalization. When external scaffold data is permanently folded into a stronger model, it represents an expansion of core authority at a fixed depth. Consider alpha geometry 2. It preserved the bounded depth pattern of its predecessor, but it successfully internalized a much stronger symbolic search vocabulary directly into its core from the outset. Benchmark gains do not imply that the hardest computational limits of the universe have suddenly collapsed into triviality. Progress is the result of layering specific, bounded verification protocols to carve out functional solutions within an intractable space. Stage descent and the polynomial hierarchy provide a rigorous mathematical language to track how bounded inference systems move toward the boundaries of feasible computation.